Hi guys, today we will be studying our last application of Gauss's law. Gauss's law had several applications, and out of which we have studied to two of the three applications of Gauss's law, and this will be the last application that as per the NCERT syllabus. So this is what we study now. It will be the field due to a uniformly charged thin spherical shell. So what is a thin spherical shell? A thin spherical shell is a sphere, very thin hollow sphere, a very thin hollow sphere having a certain thickness to it. Only a very tiny thickness to it. So it's not a thickness so as to mention two different radii to the sphere, but instead it is just a very thin sphere which would be like a rubber ball which has nothing inside, which has nothing in this region, or there is nothing outside. Obviously you are standing outside, but still the region has nothing, no material inside and no material outside. The only material that is being used is on the surface of this thin shell like sphere. So let me define a radius to the sphere. Let this be the center of the spherical shell, and from here on till here let the radius be r. I am using capital R because small letter r's are mostly used as variables. So let the radius of the sphere, the spherical shell, be r. Now what I do is I add some charge, say q, and let it uniformly spread all over this shell. Let the charge spread all over this spherical shell. So now after it has been spread uniformly onto the spherical shell surface, the charge is there everywhere on the surface. So on every point on the surface of this spherical shell we have some part of the charge q. Now we may be interested, since it has been distributed all over the surface of the sphere, let me define the sigma, or the surface charge density of the spherical shell. It would be nothing but, what was the total charge? It was q. So we have spread q charge all onto this spherical shell whose total surface area would be 4 pi r square. So let me remind you, this is what the surface charge density of this sphere is. It is sigma is equal to q over 4 pi r square, where q was the total charge that was distributed uniformly all over the shell. Now since now we need to define the electric field, we need to find the electric field due to this charge distribution. Now how was the charge distributed? The charge is now all over the surface, it's uniformly. See, I am using positive charges only. It is just for the sake of my convenience. I could have used otherwise a negative charge. There is no situational difference, any charge would suffice, but here just as an example I am using positive charge. Now the positive charge has been distributed all over the surface and has been distributed uniformly. So there are no gaps in between. Everywhere there is gap, wherever there is gap there is a positive charge filled in, provided they have sufficient space between them. which obeys their repulsion nature. All right, so we have this condition. Now the spherical shell itself divides our space into two parts. One is the inside, one is the inside of the sphere, and one is the outside of the sphere. So we have two regions around this charge configuration. One is inside and the other is outside. So how do you evaluate the electric fields in different locations of this space? We have the region inside of the sphere and region outside of the sphere. Let O be the center of the sphere, of this given sphere. Let O be the center of this given sphere. Now we can assume 2 points, one outside and the other inside. Let me just go ahead and evaluate situation where the point comes outside of the sphere. Let P be a point outside, and let R be the distance of the point P from the center of the spherical shell. So the distance OP, the distance OP is R, small r. What is the electric field at point P due to the entire charge configuration, which has the Q charge on the spherical shell, which has been spread throughout the spherical shell? So as in the previous cases, we first locate the point and using the elemental charge on the sphere. So say, let me just make it more clear. At point P, we need to first determine the direction of the electric field due to the entire charge Q or the entire spherical shell. But since the entire spherical shell is not a point charge, the electric field at the point cannot be evaluated directly. So for that, we go ahead and divide the spherical shell into small areas. Like if you have a sphere and you go ahead and check an elemental area on the spherical shell and know the charge over there, let this elemental area be very tiny area, a small area, very small area, and I am calling it small a. And in that area, what will be the charge, the amount of charge? And this area is so small that from point P, this tiny area on the sphere appears to be like a tiny dot, a point. So A is very small, and when viewed from P, it appears to be like a point. So any charge inside this area will be treated as a point charge from the point P. So what is the amount of charge in that? Since the area is A, the amount of charge, the small charge Q, will be equal to sigma times A. So that is the amount of charge on that particular area. Now due to that charge, see, let me draw that same area on this two-dimensional cross-sectional view. Let this be that area A and point P be here as seen from this figure. This area is here. Now let me just erase that R so that it does not comes in between. Also, let me get rid of this too. Okay, so from A, as you can see, the electric field due to the charge small q in the area A will be will produce an electric field at point P along this direction. It will be along the line connecting A and P, I mean the area A and the point P. So the electric field, let me use another color. So the electric field due to the point charge on the area A will be along that direction. And we can further go ahead and define electric field due to another region, say over here, and the area be similar to the previous case. Let it be A. Let it be A again. Now due to this, the electric field at point P will also be outward in this manner. Outward because we have chosen positive charges. Now you can keep doing this further, down here, up there, down here, up there, here, over here, here, over here. In every case, there will be an electric field, a couple of electric field which looks like this. In every case, the last one will have an electric field in this direction. As you can see, all of them, all of these electric fields are acting at point P due to this entire charge configuration is symmetrically pointed in that direction. So when you take the vector sum of the entire of these electric fields, these individual electric fields, they will be pointing towards that direction, because as you can see, the vertical electric fields will get cancelled out because of the number of electric fields in the upper part equals the number of electric field in the lower part, and the net electric field that will remain will be in the horizontal direction, and it will be E. This direction is actually radially outward with respect to the sphere itself. As if I draw the sphere, let me draw the spherical shell and let me pinpoint the point O, and let point P be somewhere over here. So this point P is actually a representative of any point lying outside the spherical shell. It could be here, it could be here, 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 over here, or even at the infinity. We do not care at present, but just it's a random point, so keep that in mind. Now we found that the electric field at point P was such that it appears to be radially outwards from the center of the spherical shell, the center O of the spherical shell. So which implies if we had to go on to evaluate the electric field at another point, say here, the electric field at that point due to the entire charge on this spherical shell would be again radially outward. And what about this point? On this point, it also will be radially outwards. So even here it will be radially outwards. So the matter becomes so easy. So we have no more concerns about the directions of the electric field. What we are left over with is to evaluate the electric field at point P using the Gauss's law. The magnitude part of the electric field is what we are yet to evaluate. It's like asking what will be the electric field E at point E located at a distance r at a point P outside the shell at a distance r from the center of a sphere having radius r, a spherical shell of radius r carrying a carrying a total charge q having surface charge density sigma, surface charge density sigma. So this is the problem now. So let me just use the Gauss's law. Let me draw the sphere itself. Let me draw a smaller sphere so that we can mostly use our space. So the point P was here, it was over here, the point P was here. Now we need to draw a sphere, an imaginary sphere. So the entire charge q was on this shell, not at that particular point but on the entire spherical shell. Now point P is the point of evaluation. Let me draw an imaginary, now this let me use another color, so that let me use a yellow color. So this yellow colored sphere is now actually an imaginary sphere which we call the Gaussian sphere, and point P is just a point on this imaginary surface. Now what would be the radius of this outer sphere, this imaginary sphere, from the center O, the radius will be equal to exactly r, small letter r, and that is what the radius of this imaginary sphere is. Since point P lies on the sphere and point P was already fixed to be located outside and had a radius small letter r. Now this is this yellow sphere is our Gaussian surface. Now what does this Gaussian surface, why does this Gaussian surface matters to us after all? You knew the electric field at this point P was radially outwards with respect to the point O. So this was the direction of the electric field we had. So also, if we imagine a tiny surface area on this outer imaginary sphere, let me imagine a very tiny elemental area whose magnitude is, say, dA, and let its direction, let me represent it vectorially, and its direction is, say, what would be the direction of this tiny elemental area at this point, around this point P? It will also be again radially outward. That is the peculiarity of a spherical surface. The elemental areas also are radially outwards. So that is what the direction of the elemental area dA is. So that is the direction. Now as you can see from the figure itself, if both vector E and dA are radially outwards, and if they are both parallel, which means what would be the flux through this small area? What will be the flux through this small area, this blue region? The flux at that point will be a very tiny flux, and that flux will be equal to the electric field at that point dotted with another the vector dA, the area vector dA. And since they were parallel, we just need to do the dot product evaluation. Let E be the magnitude and dA be the magnitude of the vector, area vector. Since they are parallel, the angle between them will become 0 degree, so cos of 0, and the answer to this question will become is just EdA. So this tiny flux at this particular point becomes EdA. See, this spherical surface in fact gives us another benefit, another advantage. Now point P was at a distance r, so let another point say PQRST. So let me use T. Let another point T be on this exact Gaussian sphere. Let T be another point on the sphere. If T were another point on the sphere, the point would be again at a distance equal to small r from O. Here, the O in the middle, the O is here. So this point T and this is point O, and the distance between them is r. Again at this point, as we had evaluated, the direction of the electric field would be radially outwards, So electric field is found to be radially outwards. Now my question is, what could be the magnitude of this vector E? Can you compare it with the magnitude of the vector E over here? So my question is just as simple as this. Can this E have the same magnitude as this E? Since they both are different points, their directions would be different, since at each points they must be radially outwards with respect to this point O. Of course their directions are different. My question is, if their magnitudes are same, since they lie on the same Gaussian surface, these points lie on the same Gaussian surface, does that mean the value of the magnitudes of E will be the same? The answer is yes, because if you rotate this point T over to here without changing anything, you are getting the same, this point T will coincide with the point P. Am I right? If you rotate this outer sphere, say, this point T over here will coincide with point P over here, and there won't be any more reasons for you to distinguish between whether it was point P or whether it is point T. You cannot. Or even if in the case if you rotate the point P from over here to point T over here without changing anything, you are getting point P displaced by point T. I mean point T being displaced by point P, which means again you won't be able to distinguish between whether it was point P or whether it was point T. You won't be able to distinguish between these 2 points, which implies a symmetry, and this symmetry is because this symmetric situation, even after rotating this sphere in any directions, the points become indistinguishable. You cannot separately view them as I mean, we cannot assign P to have a particular speciality over the point T. So all the points on this sphere remain symmetrical about the point O. So this is a symmetry situation, and this symmetry situation happens because of the spherical nature of the Gaussian sphere you have assumed. And the spherical nature of the Gaussian sphere along with the spherical charge distribution gives rise to this spherical symmetry. So you have got another reason to apply Gauss's law, because Gauss's law always favors charge configuration which has some symmetry in it. Now, due to this symmetry of the spherical nature of the Gaussian surface, the magnitudes of E, at point T and magnitude of point E at point P becomes equal. The magnitude of the electric field at point say T will be equal to the magnitude of electric field at point P, and see, this situation will be valid for any point on that sphere, any point on that given sphere. So provided this is the radius of the given sphere is fixed, okay, you can have another sphere for a different point. There will be another sphere. Suppose like you have another point here and you call it point PQRST, you call it U, the point U. It is farther away from the point P, so it will have another sphere of its own, and any point on that sphere will have a symmetrical situation with U. So that has to be kept in mind. Okay, so this is a very valid point because that is a very good requirement in our evaluation of the electric field. So now we go on ahead to evaluate the electric field. So the flux, the tiny flux on that near the point P was d phi, and P is just to indicate that it was the flux evaluated around the point P, around the small area, small area dA, and the differential flux was equal to EdA. See, this is a differential and this is its value, this is its equivalent value, which means to find the total flux, all you need to do is sum over all the individual contributions. See, this was the contribution of the flux at point P. So similarly, we could go on ahead to evaluate the differential flux at every point, the point T, another example, and there are like several infinite points. So all you need to do is, you cannot just directly add them, but you do is integration. You integrate these differential values and you obtain the total flux, the total flux through the sphere, through the entire sphere. This is the total flux through the entire sphere, and the sphere is obviously a closed surface. So when you integrate, there is no minus sign over here. So when you integrate this side, you will have to integrate that side also, which means you are doing is, in fact, you are doing is the integral EdA. If you might have studied in your maths class, E should be a function of the dummy index A, but no need to set that, because already E for the given radius r had a fixed value, which means for a given Gaussian sphere of radius say r, E is a constant. Who is a constant? E. The electric field E is a constant, because at any point on the given sphere of radius r will have the same magnitude. So this makes the situation easier, so that the constant value E can be taken out of the integral. Now all we need to do is add the sum over all the tiny areas. And what does this give? E remains outside. Integral of the small areas, surface areas on the sphere, when they add up together, they give is the entire area, surface area of the sphere itself. And the sphere has the area 4 pi r squared. So this is the area of the entire Gaussian surface. Now this is supposed to be equal to the integral d phi, and which was nothing but phi t. But let me go now. This forces us to use Gauss's law. Now Gauss's law states that the total flux through the closed surface, through the entire closed surface, equals q enclosed, the whole divided by epsilon 0 if it is in free space. What was our q enclosed? This yellow surface entirely covers the internal charge q. The spherical shell is entirely inside, the purple spherical shell is entirely inside the Gaussian surface. So, and the entire spherical shell carries a charge worth of magnitude q. So our q enclosed becomes q over epsilon 0. So this becomes equal to this. So what is, on comparing the both, we get E 4 pi r square equals q over epsilon 0. So nothing is left, it is just to evaluate E. Now from that equation, as you can see, from here isolating E on the left side and bringing 4 pi r square to this other side, the equation for the electric field we obtain becomes E equals q over 4 pi r square epsilon 0. Or if you neatly rearrange the terms in the denominator, you get q over 4 pi epsilon 0 r squared. So this is the electric field, 4 pi epsilon 0 over r squared. And also the direction of the electric field would become pointing radially outward. See this vector r cap, this vector r cap is actually the radial vector, the radial unit vector, whose direction is radially outward with respect to O, which means if you have a sphere and the radius of the sphere be r and this point be O, then what is the direction r cap at this point? At this point the r cap is along the radius, and this is r cap, this is the direction of r cap, and that direction itself is at which the electric field points at, and that is the exact direction at which the vector dA also points at, since they were both radially pointing outwards with respect to O. If the charge on the inner sphere was negative, the electric field would have shifted its direction into the Gaussian surface, which means E and r cap would become anti-parallel. But that would happen only when the charge on the inner sphere becomes negative. But in our case, this charge on this inner sphere was positive, so we had to take it pointing radially outwards. So that is what r cap is. So this is the vector form of the equation. The electric field E, vector electric field E is equal to the charge q on the spherical shell over 4 pi epsilon 0 r square. This exactly resembles the equation for a point charge due to the electric field due to a point charge, right? This exactly resembles that. This looks like it is not in fact a point charge distribution, but it looks like a point charge electric field, E field, right? And that happens because of this spherical symmetry. This has classically in the sense physics prior to 20th century, we assume that even a point charge had a spherical shape, but that is actually absurd because a point charge should have no shape at all since it has 0 dimensions. Still, an electron, a point particle like an electron, was assumed to be a hard sphere before 1900s, okay, before 1900s. After 1900s, the history changed and we learned quantum mechanics and knew that point particles were only ideal and they did not exist as such. Yeah, these are a few rather absurd implications, okay. So let me just go ahead and do the next evaluation. Now we evaluate the field inside the shell. Up till now we were evaluating the field, the value of the field due to the spherical shell at a point P outside the shell. So if we had a spherical shell, I mean I shouldn't be using because yellow would represent a Gaussian sphere. So we had a spherical shell and let point P be outside and O be the center and distance from the center to the point P we were evaluating the electric field at this point, and this point lied outside the outside region or the outside of the spherical shell. Now we evaluate for a point. Now let me evaluate for a point. Let me just expand it. Yeah, zoom it in. Now let me evaluate for a point P. Say let this be point P. Now this point P, let this be the center O. This point P is inside the spherical shell. The spherical shell itself had a radius, thin spherical shell had a radius r, and let this point P in the inside be at a distance again small r. Let it be at a distance r from O. My question is, what is the electric field at the point P due to this outer shell, the charge on the outer shell, this entire charge configuration? What is the electric field at the point P here inside due to the entire charge configuration, entire charges on the spherical shell? What will it be? So to evaluate that, we again apply the Gauss's law. Basically, what you require for a Gauss's law, to apply Gauss's law, at first all you need is a charge configuration, or whether it exists or not is not a matter. The first thing you need to do is to imagine a proper, let me use the yellow color so that it does not confuse us with your convention. We need to draw a proper imaginary Gaussian surface that suits the situation, and that point, that particular point of interest P should lie on this this given the Gaussian surface you have imagined. Now for our purpose I am using a spherical surface, a spherical imaginary Gaussian surface. See, I need not keep repeatedly saying imaginary Gaussian surface, because Gaussian surface are by default assumed to be imaginary. So let this be the spherical shell. Now what is the charge, what is the Gaussian surface is this. Now what is the charge that this Gaussian surface encloses? Is there any charge inside this Gaussian surface? There is charge outside, but is there any charge inside the Gaussian surface? No, there is no charge this particular Gaussian surface has inside of it, which means when we go ahead to apply the Gauss's law, if you have a Gaussian surface and the Q enclosed, I mean, like, let me just draw a bit more larger circle. I mean a sphere. It's not a circle, it's two-dimensionally appeared to be sphere. There is no Q enclosed. The Q inside is 0, which means after evaluating, then the flux total inside would be Q enclosed by epsilon 0 according to the Gauss's law. But Q enclosed itself is 0. Numerator 0 means the entire term on the right hand side becomes 0, which means total flux through that particular surface becomes 0. If the total flux is 0, then the total flux was found to be E 4 pi r square, and this becomes 0. Since the surface area of the Gaussian sphere is not 0, since r is not 0, the only possibility is that electric field is 0. And that's all, guys. The entire electric field inside a charged spherical shell is nothing but 0. If you have a spherical shell, if you had a spherical shell like this and there was some charge Q all over it, the electric field inside becomes 0 and there is no electric field inside. This can be found even using the Coulomb's law. All you had to do was to divide all this this entire sphere into smaller tiny point like region, and then assumed a point. As you keep on evaluating the electric field, they vectorially cancel out. If you want any further explanation on that, ask me. Now go outside from the center O of the entire sphere at a point at a distance r. The electric field outside outside the spherical shell will be E equals Q times 4 pi epsilon 0 r square. This will be the electric field outside. So electric field inside becomes 0. So inside it is 0 and outside it is not 0. So that's all, guys. So that was the third application of Gauss's law, and we would be moving on to the next chapter, which deals with electric potentials and electrostatic energy. Thank you for watching the video. Please do comment your opinions in the comment section below. Thank you.